All right, let's go ahead and get started.
Recording in progress.
Hello, everyone, and welcome back. Today, we're continuing on with the MHF4U course. This is the grade 12 Advanced Functions University, and we are on Unit 2. This is going to be Lesson 8, Part 1 of 2. So typically, usually from experience, that students tend to forget about the special angles when they take this course. And so we're going to be separate this into two parts, where in the first part, we're going to develop and apply some of the basic angles, and then some of the special angles in degrees and radians. And then we'll have a look at something called a coterminal angle. And so consequently, the topics we'll be covering will be the special angles 0, 30, 45, 60, 90, 180, 270, 360, and their radian equivalent, as well as terminal angle. On the left time, we'll study function values at these values. So essentially, we'll be taking these special angles and reflecting them in other quadrants and applying the cast rule. And in general, we only have one success criteria for today, which is you'll be able to develop and apply the special angles for trigonometry. And so, as a review of last time, if we had a right angle triangle, and we have an angle of interest, say angle theta, and we're given some, say, x, y, and r, you could say that sine theta is equal to the opposite over hypotenuse, which would be y over r. Cos theta is equal to the adjacent over opposite over hypotenuse, which will be x over r. Tan theta is equal to the opposite over adjacent, which was y over x. Cosecant of theta is the reciprocal of sine theta. So instead of y over r, we have r over y. Secant theta is the reciprocal of cosine theta. So it's given by r over x. And cotangent theta is the reciprocal theta. So its ratio is given by x over y with respect to the unit circle. And so that's what we need now in order to continue. But first, we're going to develop the special angles. And so we do want to, at this point, take our time to go ahead and define what an exact angle is, or more specifically, an exact answer. Exact answer is a value that is not approximated or rounded. So for example, if I were to take, say, 1 divided by 3, this would be equal to 0.33333, repeating forever. And at some point, we might just kind of round this off at some point. Okay, this 1 over 3 would be your exact answer. So if you needed to represent the decimal expansion 0.333 repeating, you'd use 1 over 3. The rounded answer is what you decide to terminate at. So in this case, we rounded to the 2 decimal places. So this would be our rounded answer. For our purposes, we are interested in exact answers for today. And so we're going to develop the special angles. And for this, there's two kinds of special angles for us to be worried about. There is the 45, 45, 90 triangle, which is coming up later. And for now, we have the 30, 60, 90 triangle. So how do we get this? So what we do when we want to develop the 30, 60, 90 triangle is we start with an equilateral. And so an equilateral triangle, as a quick definition, has all the same sides as well as all of the same angles. And so we can make the side legs whatever we want. Say, for example, we can make them all 3, or we could say the side lengths of all of this are going to be, say, 10. In truth, it's not going to matter because of what we're focused on is the ratio that they'll form. So it's actually a lot easier from a math perspective is we actually just have a side length of 2. And so we're going to be using 2 units to represent our triangle. The next thing we're going to do is drop a perpendicular line from the top of the triangle down to its base. It's also called an altitude. And so when we do this, 2 things happen. 1, we're going to disregard half the triangle. And 2, that's good. We're going to be able to fill in their measurements. So now consider this triangle. So here, this is the subduct triangle. I know that the top angle is 30 degrees because half of 60 is 30. Okay. And so I know that this hypotenuse is 2 because remember, that's what we made the assumption as. And this could have been 1 or what have you, but 2 is actually the easiest one to think about. Now, how long is this side going to be? Say this one side at the base of the triangle I had labeled X. Well, if you notice, based on the above equilateral triangle, I had divided this triangle into 2 equal parts. So the base of this triangle is actually going to be just 1. And so now we're interested in the height of this triangle. So how tall is this going to be? That one's not so obvious. We actually have to use Pythagorean theorem to figure that out. And so if we take 1 squared plus h squared, well, I guess I should mention in general that if a squared plus b squared is equal to c squared, where a and b are the corresponding legs and c is the hypotenuse, the height of this triangle will be given by, say, h squared. The base of this triangle will be given by 1, and the hypotenuse will be given by 2. So substituting those values, we have h squared plus 1 squared equals 2 squared. 1 squared is 1, and 2 to the power of 2 is going to be 4. Minusing 1 from both sides, we have h squared is equal to 3. And if I take the square root of both sides, we find that h is equal to the square root of 3. In fact, the height of this triangle is going to be the square root of 3. So what's so special about this now? Well, 2, 1, square root of 3. I can now start asking some interesting questions. And so what if I want to know, say, sine of 30 degrees? Well, for 30 degrees, that makes this 1 the opposite, the 2 the hypotenuse. So sine of 30 degrees should be equal to the opposite over hypotenuse, which means it's going to be equal to 1 over 2. Exactly 1 over 2. And you notice here, if I type in sine of 30, I get 0.5 or 1 over 2. Why stop there? What about cos of 30 degrees? Well, that's equal to the adjacent over hypotenuse. So the square root of 3 becomes the adjacent. And so that'll be square root of 3 over 2. And so if you type in cos of 30 degrees, you get this 0.86602 number. But importantly, if you type in the square root of 3 over 2, it's exactly that number. Depending on the type of calculator you may have, you might actually be able to type in cos of 30 and get exactly root 3 over 2. So for example, my personal calculator does that. However, the Desmo scientific calculator does not. Unfortunate, but that's okay. So we know this works. We can also do, say, tan of 30 degrees. So that's going to be equal to the opposite over the adjacent. So in this case, the opposite is 1, and the adjacent is the square root of 3. So if I type in tan of 30, I get 0.577. And if I take 1 divided by the square root of 3, I get the exact same solution. As a note for us, sometimes you'll see this notation. We can rewrite the 1 over the square root of 3 as the same thing as the square root of 3 over 3. So why does this work? Well, if you were to take 1 over the square root of 3 and multiply the numerator and denominator both by the square root of 3, 1 times the square root of 3 is 3. The square root of 3 times the square root of 3 is 3. Another way to think about that is what number times itself gives me 3. So that's going to be that solution. This is what we call rationalizing the denominator. And there's a lot of reasons why we do this, but for the moment, they're not too important, but just note that this is an alternative way that we can write this. And following from this, if we were so interested, we can also get things like, let's write this in blue. We can also get things like the cosecant of 30 degrees. So that's going to be equal to the hypotenuse over the opposite, which is going to be 2 over 1, which is just 2. And so if you have, say, sine of 30, you can get cosecant of 30. So secant of 30 degrees would be instead of adjacent over opposite, adjacent over hypotenuse, it becomes hypotenuse over adjacent, which will be 2 over the square root of 3. And lastly, instead of tan 30, we could have cotangent of 30 degrees, which will be the adjacent over the opposite, which will be the square root of 3 over 1, which is just the square root of 3. And so we have exact solutions for everything involving a 30-degree angle. But there's nothing special about that particular angle. So we did 30 degrees. And when I say nothing special, I mean, we could have also done the similar exercise, but chose 60 degrees instead. So if I wanted to, I don't quite have the space for it here, but I did summarize it down below. We could answer questions like, what is the sine of 60 degrees? Well, based on the 60 degrees, the root 3 over 2 would be the opposite, and the 2 would be the hypotenuse. So this would be equal to, say, the square root of 3 over 2. And if I type in sine of 60, we end up getting that 0.866 number, which is the equivalent to the square root of 3 over 2. And so we can develop these special angles in degrees. And this is what we call the 30, 60, 90 triangle. Okay? This same exercise can be developed in radians as well. So when we have our triangle, there's our equilateral triangle. Instead of an angle of 60 degrees, we would have an angle of pi over 3. So remember, if you take 100 and if you take 60 degrees and multiply it by pi over 180, this is equal to pi over 3. And so if you were to divide this down, you would still have this 30, 60, 90 triangle, except now you would have the 60-degree angle would be pi over 3, and the 30-degree angle would be pi over 6. The math from all of this would still follow the same. So for example, if I wanted to know tan of pi over 3, based on say that the root 3 would be tan of pi over 3 would be equal to root 3 over 1, which will be just the square root of 3. And on your calculator as well, if you were to type in tan of pi over 3, you would get this 1.73 number, which is the same thing as the square root of 3. Okay, and just to reemphasize this point, suppose I was interested in, say, sine of pi over 3. That's equal to the opposite over the hypotenuse. So that'll be equal to the square root of 3 over 2. And on my calculator, if I were to type in tan of pi over 3, I get that 0.866 number, which is the same thing as the square root of 3 over 2. Consequently, they are the same. Okay, so the triangles are easier to develop in degrees, but they also are perfectly applicable for radians. And so I've summarized the basics down here below. And so here, if you have sine of 30 degrees, that's the same thing as sine of pi over 6. That's equal to a half. Cos of 30 is equal to cos of pi over 6, which is equal to root 3 over 2. Tan of 30 is equal to tan of pi over 6, which is equal to 1 over root 3. And the resulting ratios, sine 60, cos 60, tan 60, and their corresponding ratios. The textbook has these as well, but the textbook just tells you what they are. They don't develop these just because they don't have time to do such a thing. But we are here in the course, so we do have some time for this. Now, another triangle exists. This one is called the 45, 45, 90 triangle. And the reason why it's called a 45, 45, 40, 90 is that we are working with an isosceles. And I guess it should be a bit more accurate. We're going to call this a right isosceles triangle. So this is a triangle with a right angle, and we've got here two 45-degree angles, and this is 90. You could also work this out intuitively, because if one side is 90, then the other two sides must add up to make 90, must be the same. Consequently, it must be 45, 45. And through a similar exercise, you might be wondering, what's a good side length for this? As it turns out, 1 is an excellent side length to be using. And so we can figure out the hypotenuse, say little a, by saying that 1 squared plus 1 squared equals little a squared. 1 plus 1 is equal to a squared. 2 is equal to a squared. Taking the square root of both sides, the square root of 2 is equal to a. Okay. And so now we can ask interesting questions like, say, for example, what is sine of 45 degrees? Well, we actually can choose either one of these. Suppose, let's label this as our angle of interest. This becomes the opposite, the adjacent, and the hypotenuse. So sine of 45 is the opposite over hypotenuse. So this will be 1 over the square root of 2. So if I type in sine of 45, I get 0.850 something, something, something. Oh, sorry, in degrees, I get 0.707. And if I take 1 divided by the square root of 2, I get the exact same solution. This is also true for if I were to type in, say, cos of 45 degrees. Cos of 45 would be the adjacent over the hypotenuse, which would again be 1 over the square root of 2. And if I were interested in tan of 45, would be the opposite over the adjacent, which is going to be 1 over 1, which is 1. And so the reason why tan of 45 degrees is equal to 1 is because its ratio of opposite to adjacent are the same, meaning that it's going to be 1. Insofar as both the sides are of equal length, therefore the ratio between them will be 1. And so if we type in tan of 45, that's why we get 1. Just as a little note for us as well, similar to last time, some textbooks will write it just as 1 over the square root of 2, but they may rationalize this as well and write this as the square root of 2 over 2. And these are the same thing. So if I take 1 divided by the square root of 2, that's the same thing as the square root of 2 over 2. So we get the exact same solution. Okay. This can also be done in degrees. So recall 45 degrees is equal to pi over 4. So if we were to take 45 and multiply it by pi over 180, That's equal to 45 multiplied by pi over top of 4 multiplied by 45. And we get that pi over 4 that we studied back in lesson 5. And so knowing this, these 45 degrees become pi over 4. And from here, the exact same exercise plays out where we can evaluate sine of pi over 4, cosine of pi over 4, or tan of pi over 4 as the corresponding ratios that we talked about earlier. This triangle is easier to work with, but that's why we do start with the more difficult one first. Okay. And so now we're going to apply what we know. So we're going to evaluate each of the following to determine the exact value of these. Okay. And what some people like to do, and they'll draw a right angled triangle out for themselves, and they'll just kind of write down the measurements ahead of time. And so we're able to do this because you just draw a right angle. You know that the bottom angle is going to be, say, 60 degrees, which is going to be pi over 3. And so then you know the other one is going to be 30 degrees or pi over 6. Later, and it's not in this lesson, but in future lessons, I actually have little right triangles that we're going to be using for this. So these are worth committing to memory. Or what you can do is just kind of draw out this little triangle to help you remember what these are. The pi over 4 one is fairly straightforward. Okay. So cosine of pi over 3. So pi over 3 is going to be the 60 degree angle. So it's going to be 1 over 2. So it's just going to be a half. And if you're not sure, you can type these into the calculator. This time we have to work in radians, however. So if I type in cos of pi over 3, I can get that 1/2. Tan of pi over 4 is just 1. Sine of pi over 6, so that's the 30 degree angle up here. So that's going to be 1 over 2. Secant of pi over 3. So remember, this is the same thing as 1 over cos of pi over 3. So as a little note for this, we can say cos of pi over 3 is equal to what? Well, that's the answer we got from above here, right? So that's going to be equal to 1/2. And so secant of pi over 3 is just the reciprocal of this. So it's just going to be 2 over 1, which is just 2. Similarly, cotangent of pi over 4 was the reciprocal of the answer of 1. Well, that's just going to be 1. And using the answer from earlier, cosecant of pi over 6 is the reciprocal of 1 over 2. And so that's going to be equal to 2 over 1, which is just 2. So applying these are relatively straightforward as long as you already have the primary trigonometric ratio. And if you don't have that, just go ahead and solve for the angle in the primary trigonometric ratio and then take its reciprocal. Okay. And so we're now going to consider some more of the special angles. So we're going to have a look at an angle of 0 degrees or 0 radians. In truth, it doesn't matter which, it's going to be the same thing. And so we can just use the calculator. So here, sine of 0 is 0, cos of 0 is 1, and tan of 0 is 0. So while the calculator answer tells us that these are the solutions, so point, we're going to get 0, 1, and 0 with respect to sine 0, cos 0, tan 0. It's much more interesting to figure out, well, why is that the case? So let's consider this triangle shown right. So this is a standard triangle shown on a circle. The circle is radius of, I think it's supposed to be 5, but for our purposes, we're just going to say the radius is just 1. So that means the point out there is 1. This will be -1, 1, and -1. And so what we're interested in is what happens as theta gets closer and closer to 0. And so this point P is going to be dragged down and move closer and closer and closer and closer to 1. So what happens in this case? Well, the radius of this triangle doesn't change. It'll remain 1 the whole time. The y-coordinate, as we get closer to 0, the height of this point becomes 0. The x-coordinate actually becomes the same as the radius eventually, because as we're moving the point downwards, the x-coordinate gets longer and longer and longer until it reaches 1. And so we have a triangle whose adjacent is 1, whose opposite is 0, and whose hypotenuse is 1. And so using our triangle, if sine of 0 is the opposite over hypotenuse, that's equal to 0 over 1, which is why it's equal to 0. Cosine of 0 is the adjacent over the hypotenuse, which is going to be 1 over 1, which is 1. And tan of 0 is going to be the opposite over adjacent. The opposite is 0, and the adjacent is 1. So 0 divided by 1 is 0. And we're going to be using similar logic to go ahead and calculate sine of 90, sine of 180, sine of 270, and then eventually sine of 360. You can pause the video now and go ahead and try out some of those and see how you do. Okay, let's continue on. Okay, so similar exercise, but now we're going to be talking about a 90-degree angle. And again, you could just use the calculator to figure this out. So sine of 90 seems like it's going to be equal to 1. Cosine of 90 is going to be equal to 0. And tan of 90 is undefined. So again, that's not interesting because perhaps, well, how do you get that? So let's have a look. So in our diagram, we're going to make the same assumptions as before. We're going to make this a unit circle. And in fact, it doesn't need to be a unit circle, but it's easier to think about it that way. And what happens? So we're looking at theta as we approach 90 degrees. So we're taking this point P and dragging it up to the coordinate 0, 1. So what happens here? The radius is 1. That doesn't change. The y value goes up and up and up and approaches a height of 1. The x value has a horizontal distance of 0. So we have this kind of configuration where it's still a triangle where instead of the height being 0, the x value is now 0. So sine of 90 is equal to the opposite over hypotenuse, which is going to be equal to 1 over 1, which is 1. Cos of 90 is the adjacent over hypotenuse, so this will be 0 over 1, which will equal 0. Tan of 90 is the opposite over adjacent, which is why it's undefined, because we can't have division by 0. Okay? Now, this is also true if you were to type in, say, tan of pi over 2 in radians, this would also be undefined as well. Okay, and so here I have summarized so sine of 0 is 1, cos is 1, tan of 0 is 0, sine of 90 is 1, cos of 90 is 0, tan of 90 is undefined, and their corresponding radian equivalent. Okay, so let's apply what we know. So again, there's the reciprocal ones are in here, but once we know what the primary ones are, we can then get the reciprocals. So I'm going to show this in 2 steps. Remember, cosine of 0 is equal to 0 over 1, which is 0. Tan of 0 is equal to 0 over 1, 0. cos of 0 is equal to 1 over 1, which is 1, because the adjacent is going to be the same as the hypotenuse. Tan of 0 is equal to 0 over 1, which is 0. And sine of 0 is going to be equal to 0 over 1, which is 0. Not sure why I put them this way instead of the traditional way, but here we are. Okay, so secant of 0, so that's going to be the reciprocal of 1 over 1. So secant of 0 is going to be 1 over 1, which is 1. Tangent of 0 is going to be 2 over 0 is tangent of 0 is going to be equal to 1 over 0, which is undefined. So with the reciprocal trigonometric ratios, we're going to run into the situation where we're going to end up with division by 0. So the reason why I wanted to take the time to show the 1 over 1, the 0 over 1, and the 1 over 0 was with respect to the reciprocal trigonometric ratios. Okay. What about cosine of pi over 2? That's going to be equal to 0 over 1, which is 0. And if you're not sure, you can also just reference the work that we did from above to help you solve these. Okay. Tan of pi over 2, that's going to be equal to 1 over 0, which was undefined. Sine of pi over 2 is equal to 1 over 1, which was 1. Secant of pi over 2 is the reciprocal of 0 over 1. So that'll be 1 over 0, which is undefined. Now, whereas tan was undefined at pi over 2, cotangent is actually well defined. We can flip 1 over 0 to become 0 over 1, which is just 0. And cosecant of pi over 2, the reciprocal is 1 over 1, which is just 1. So as soon as you enter these 90-degree angles and subsequent multiples of 90 degrees, some of the ratios end up being undefined because you have division by 0. Okay, similar exercise. And now at this point, all I've done is I've now included the reciprocal trigonometric ratios. So an angle of 180 degrees or pi. And so again, we're interested in this angle. And we want to see what happens to the point P, which is given coordinates of x comma y, as it trends downwards. And so as a reminder, we're going to again use a unit circle. It's not necessary. You could say have the circle could have a radius of 5, but you would end up with 5 over 5, for example. Move downward. Well, the whole component will become the same as the radius, except it's going to be in the negative direction. So it'll be an x component of -1. So we have a 180-degree angle is going to have a triangle of 0, -1, and 1. Note that actually still fulfills Pythagorean theorem, because 0 squared plus -1 squared is equal to 1 squared. So -1 times itself is 1, 1 squared is 1. So this still has no problem fulfilling the conditions of Pythagorean theorem. Okay, sine of 180 is going to be the opposite over hypotenuse. So the opposite is going to be 0 over the hypotenuse, which is 1. So it'll be 0. Cos of 80 will have adjacent component of -1 over 1, which will equal -1. And tan of 180 will be equal to 0 over top of -1, which will be equal to 0. And so now cosecant of 180, instead of 0 over 1, it becomes 1 over 0, which will be undefined. Secant of 180, the reciprocal of -1 over 1 is 1 over -1. So this will just be -1. And cotangent of 180, the reciprocal of 0 over -1, is going to be -1 over 0, which is undefined. Okay, and this is again true for 180 degrees or pi. So if I type in sine of 180, I get in degrees 0. And if I type in sine of pi in radians, I get 0. The Desmos calculator just will shift all of the previous calculations you had above into either degrees or radians. Okay. Similarly, let's have a look at an angle of 270 degrees. So again, we have the point P, x comma y. We're going around the unit circle. We're now moving in this direction. And we want to see what happens as we get closer and closer and closer to an angle of 270 degrees. We're going to make the same assumption and say we have sides of a unit circle of 1. So what happens here? Well, as this coordinate, we drag it, x comma y, closer to 0 comma -1, what happens? Well, the radius is 1, that doesn't change. The height of this triangle will eventually reach -1, and this will have a horizontal component of 0. So an angle of 270 degrees will be in, so an angle of 270 degrees will have a right angle triangle of 0, -1, and 1. And so sine of 270 is the opposite over hypotenuse. So remember, the opposite is going to be -1. So this will be -1 over 1. So sine of 270 is -1. So if we type in sine of 270 in degrees, you can see we get that -1. Cosine of 270 is going to be 0 over 1, which will be 0. And tan of 270 is going to be -1 over 0, which is just going to be undefined. And so if we type in tan of 270, we can get that undefined. Or if we type in tan of 3 pi over 2 in radians, we still get that undefined because they're equivalent. Okay. Cosecant of 270 is the reciprocal of the opposite over hypotenuse. So instead of -1 over 1, we have 1 over -1, which will be -1. Secant of 270, instead of 0 over 1, we get 1 over 0, which is undefined. And cotangent of 270 is going to be equal to 0 over -1, which will be just equal to 0. Okay. Lastly, but not leastly, since the circle is 180 degrees, it seems like it would make sense for us to study an angle of 360 degrees. And so let's have a look. So again, we now, assuming the same circumstances, unit circle of 1, focus on the point x comma y, and we want to know what happens as we move the point closer. The radius of this will remain 1. The height of this coordinate as we approach 1 comma 0 becomes 0. And for the x value, it becomes the same as the radius, which is +1. So sine of 360 degrees will be equal to the opposite over hypotenuse, which will be 0 over 1, which is 0. Cos of 360 will be the adjacent over hypotenuse, which will be 1 over 1, which is 0. Tan of 360 will be the adjacent over the hypotenuse. Sorry, will be the opposite over adjacent. So that's going to be 0 over 1, which is 0. And I also did just tell you 1 divided by 1 is 0. These things happen. Okay. So cosecant of 360 is the reciprocal of 0 over 1. So that'll become 1 over 0, which is undefined. Secant of 360 is the reciprocal of 1 over 1, which is 1 over 1. So this will be equal to 1. And cotangent of 360 is going to be equal to 1 over 0, which is going to be undefined. Nope, just as a small notational purpose. We don't say equals undefined, we just say it is undefined. So that's why I just use this arrow to signify that this is undefined. So is there anything special about 360? Well, if you have a look at all of these, it appears to be some variation of 1, 0, -1, and undefined. But if you were looking carefully, you might have noticed that 0 degrees was exact, you know, this for sine, cos, and tan of 0, 1, 0. That ended up being exactly the same 0, 1, 0 for 360. And so as it turns out, an angle of 0 degrees is the same as 360. So if I type in sine of 0 degrees, that's the same thing as sine of 360 degrees, which is 0. So sine of 0, 0, sine of 360 in degrees is also 0. This is the same thing as me saying in radians, sine of 0 is the same thing as sine of 2 pi, which will be 0. So if I type in sine of 0 and sine of 2 pi, these are the same. Is there anything special about this? Actually, yes. As shown by this, we enter into a topic called a coterminal angle. As shown by the unit circle above, sine and cosine repeat every 2 pi and 360. So for both sine and cosine, and then as well as cosecant and secant, when you add or subtract a multiple of 360 degrees, or 2 pi, depending on what unit, whether you're in degrees or radians, the ratio remains the same. So what does this mean? So let's consider a 40-degree angle. And if we take 40 plus 360 degrees, we get 400. And if we take 400 plus 360 degrees, we get 760. So what I'm telling you is that all three of those would be the same if we type in, say, cos of 40. That'll be the same thing as cos of 400. Which will be the same thing as cos of 760. And we can use a calculator to verify this. So cos of 40 is about 0.766. Cos of 400, 0.766. Cos of 760, also 0.766. And the reason for that, with respect to a geometric perspective, if you imagine a 40-degree angle in quadrant 1, if you were to go around the circle again and you rotate it 360 degrees, you end up exactly where you started. So this would end up being an angle of 400 degrees. And if you wanted to go around the circle again, you still end up in exactly the same spot, but you just tacked on another 360 degrees, which means you'd have an angle of 760 degrees. This is true for any value you pick, 0, 13.4, what have you. So for clarity purposes, is if you do sine of 13.4 degrees, that's the same thing as sine of 13.4 plus 360 degrees. You would still get the exact same answer. Comically, or in this case, it should be noted that if I were to take 13.4 and minus 360 degrees, you would still get the exact same solution, even though it would be a negative angle. And so this section I call the coterminal angles, where some examples I gave you were sine of 0 is equal to sine of 360 equal to sine of 720, and so forth. So you could plus or minus multiples of 360 degrees. And the way we describe that is we say plus or minus 360 to n, where n is an integer. So that means like numbers like 1, 2, 3, as well as 0, -1, -2. And in radians, you can do the same thing. So you might have sine of 0 is equal to sine of 2 pi, 4 pi, 6 pi, -2 pi. And then if you take pi over 2 and add 2 pi, you get 5 pi over 2. Add 2 pi, you get 9 pi over 2, and so forth. So if I type in sine of pi over 2, this is the same thing as sine of 9 pi over 2. And so you could take sine of pi over 2 and add on some large multiple of 2 pi and end up getting the same thing in the end. Maybe if you're watching this online, I'll make it a bit more clear and say some multiple of 2 pi. Like tangent has the same thing, except it's 180 degrees instead. So exactly the same. Tan of 30 degrees is equal to tan of 30 plus 180, which is the same thing as tan of 30 minus 180. So here they necessitate the use of 180 degrees instead. We will study in a later lesson why that's the case. Okay, so for example, 3, we're going to just determine 3 angles that have the same ratio as the following. So for example A, it's going to be sine of 50. So this will be the same thing as, say, sine of, so we could just take 50 plus 360. So this will be 410. We can take 410 plus 360. So it will be sine of 770. We can also take 50 and minus 360. So this is the same thing as then of sine of negative 310 degrees. Pi over 4, a bit trickier because it's in radians, but it's still done the same way. So if we take 2 pi and add it to pi over 4, we get cos of 9 pi over 4. Because remember, 2 pi is the same thing as 8 pi over 4. Adding 8 pi over 4 to cos of 9 pi over 4, you end up with cos of 17 pi over 4. You could also take pi over 4 and minus 2 pi, in which case you would end up with cos of negative 7 pi over 4. Similar exercise can be done with tan of pi over 5. So recall that 10 pi over 5 is the same thing as pi over 5 is equal to 2 pi. So tan of pi over 5 is the same thing as tan of 11 pi over 5, which is the same thing as tan of 21 pi over 5, which is the same thing as, say, pi, which would be 5 pi over 5 is just pi. So this could be the same thing as, say, tan of 6 pi over 5. And just to verify one of these, if I take tan of pi over 5, I get 0.72. I'm saying that that's going to be the same thing as tan of 6 pi over 5. And so it is. Okay. And so we can use the idea of a coterminal angle to evaluate angles greater than 2 pi or less than 2 pi. So for example, what is cos of 2? Well, we're going to utilize a coterminal angle. So cos of 9 pi over 2 is quite large. However, I can rewrite what I can do with 9 pi over 2 is minus just 2 pi, right? So this will be equal to cos of 2 pi is the same thing as 4 pi divided by 2. So if I take 9 pi minus 4 pi, that ends up giving me 5 pi over 2. That's still outside of 0 to 5 pi over 2 minus 2 pi, which will be equal to cos of pi over 2, which is going to be 0. Alternatively, you could just use a calculator for this, but I do encourage you to use the logic to show why these answers are the way they are, just so that way you gain a better understanding. Cotangent of 9 pi over 4, well, we can minus off, we're going to minus off 2 pi, so this is going to be the same thing as cotangent of, and the reason why I'm minusing off 2 pi is just because I only have a few minutes left. So instead of going through the logic of 2 pi, we'll just skip 2 steps. So this will be the same thing as, now note, 8 pi over 4 is the same thing as 2 pi. So cotangent, well, we can write cotangent better. So cotangent of 9 pi over 4 minus cotangent of pi over 4. Remember, cotangent of pi over 4 is the same thing as 1 over tan of pi over 4. So remember here, we're using the reciprocal relationship that we learned about earlier. And tan of pi over 4 is just 1. So this is just 1 over 1, which is 1. So not too bad. Lastly, we have sine of negative 7 pi over 4. And so we can write this as sine of negative 7 pi over 4 plus sine. Now remember, 2 pi is the same thing as 4. So negative 7 plus 8 is 1. So this will be the same thing as sine of pi over 4. And sine of pi over 4 was the same thing as 1 over root 2. So if I take 1 divided by root 2, this was the same thing as sine of pi over 4 in radians. Now, importantly, as a final note for you, always express answers or solutions exact form when possible. Okay, so while it is correct to say that sine of pi over 4 is equal to 0.707, something, this would not get you a right answer if the question wanted you to write this in exact form. It's a numerical solution, which would be 1 over root 2. So when it's in exact form, that means it wants the fraction answer. Okay, don't write down the decimal. So if we scroll back up, so we developed the special angles of 0, 30, 45, 60, 91, 82, 73, 60, and the radian equivalent, and we had a look at those coterminal angles. That'll do us for today. On the lesson of next time, we're going to be looking at function values of these angles in different quadrants. As always, if you have any questions, comments, or concerns, do feel free to reach out, and we'll get back to you next time. And Goodbye for now.